In this video, I want to do a lightning review of the basic tools for calculus, for basic tools of differentiation specifically. There are 7 basic tools you need to be able to differentiate any function anybody can throw at you. First, we're going to go over the power rule, then something called the product rule, a closely related tool called the quotient rule. Oh, that's also a rule. And the last rule is going to be the chain rule, which is probably the most powerful one of the 4. And then I'm going to quickly go over some special cases, derivatives of exponential functions, logarithmic functions, both because they're special cases of derivatives and because they come up so often when you're modeling populations, and finally a brief discussion of derivatives of trig functions. So let's take a really general power function and say f of x is x to the n, some number n. To take the derivative of any power function, so f prime at x, we're going to take the exponent, move it down in front, so now it's n times x, and we're going to subtract 1 from the original exponent, n minus 1. So, for example, if you had a function y is equal to 3x to the 4th, then the derivative of that, dy by dx, would be 4 times 3, x to the 3rd, which is 12x cubed. Or if I had a function p is equal to 1/3 x to the 6th, the derivative of that, dp by dx, would just be, bring the 6 down, 6 times 1/3 times x, and 6 minus 1 is 5, so 2x to the 5, and so on. I could prove this to you, but I need to use a couple of special cases that are not going to be till the end of this video. So at the very end, we'll come back and prove the power rule to you very quickly. So now that you've learned the derivative rules for exponential and logarithmic functions, I can show you the quick proof for the power rule. So we're going to start off with the fact that x to the n is equal to e to the n times the ln of x, a natural logarithm of x. If you don't believe me, try taking the natural logarithms of both sides of this equation and see what happens. So, by definition then, the derivative of x to the n is going to be equal to the derivative with respect to x of e to the n ln n. We know by the rules for derivatives of exponential functions that that's going to give us e to the n ln n back again, n ln x back again, times the derivative of n ln x. Which, by the rules of derivations of logarithmic functions, we know is just going to be n over x. Going back to the beginning, e to the n ln x is equal to x to the n times n over x, which gives us n times x to the n minus 1, the power rule. The product rule helps us take derivatives when your function is a product of 2 other functions. Let's say, for example, I've got my function y, and it's a product of 2 other functions, f at x times g at x, 2 other functions of x. It turns out the derivative of that function, dy by dx, is equal to the derivative of the first one times the second one, plus the derivative of the second one times the first one. I guess that's a bit of an odd mix of notations. I should probably have written that df by dx times g at x plus dg by dx times f of x. Anyway, you can skip ahead here and take my word for it, or I'm going to go over a short proof to explain why this is true. So I want to find the derivative, d by dx, of f at x times g at x for two arbitrary functions of x. Well, by the definition of the derivative, that should be the limit, as h goes to 0, of f at x plus h times g at x plus h minus f at x times g at x all over h. And here's where I'm going to pull a little trick. I'm going to extend my fraction here, and I'm going to add f at x plus h times g at x, and I'm going to subtract it, so I haven't actually changed anything about the value of my expression. But it lets me rearrange like this. Now I can say the limit as h goes to 0. So now on top I'm going to rearrange a bit. I'm going to take f at x plus h times g at x plus h, and I'm going to subtract, in blue, I'm going to subtract one of those, f at x plus h times g of x. Now I'm going to add the other one, f at x plus h times g at x, and then subtract f at x times g of x. And that's all still over h, excuse me. So if I rearrange this yet again, I'm going to change it to be the limit as h goes to 0. I'm going to take the 1 over h out over here. So now I've got f at x plus h times g at x plus h minus g of x plus h plus g of x times f at x plus h minus f of x. Now we get to do a little bit of cancelling. So in the limit as h goes to 0, f at x plus h is just f at x. And the limit as h goes to 0 of g to the x plus h minus g to the x all over h, well, that's just g prime at x. Over here, the limit as h goes to 0 is g of x because it doesn't depend on h at all. And this expression over here, f at h plus x minus f at x, well, that's just f prime at x. And so we have our product rule. I'm just going to go back here and do a quick example. So let's say I've got my product function, f at x is x squared times 1 minus 3x cubed. So we can look at it as a product of two functions, x squared and 1 minus 3x cubed. So I can apply my product rule and say, okay, df by dx is going to be the derivative of my first function, which is just 2x, times my second function, 1 minus 3x cubed. And then it's going to be plus f, my first function, times the derivative of the second one, which is minus 9x squared. Which gives me altogether 2x minus 6x to the 4th minus 9x to the 4th, which is 2x minus 15 times x to the 4th. And we can check that by going up back to my original function, and instead of using the product rule, I can just multiply this out and get, I could have written it as x squared minus 3x to the 5th, and the derivative of that is just 2x minus 15x to the 4th. It works! And a lot of the time, your product functions are not going to be as simple as this one, and it's much easier to just use the product rule instead of trying to multiply out all of the things in your function. Next up we have the quotient rule, which, as you can imagine, is very closely related to the product rule. So let's say instead of having a product of two functions, I've got my two functions f at x divided by g at x. And I want to find the derivative of this quotient function. Well, if you're not interested in the proof, I'll just skip to the end. It's the derivative of the first function times the second minus the derivative of the second function times the first function minus the derivative of the second function times the first function all over the second function squared. And I think this is much easier in the prime notation, so it's f prime of x times g of x minus g prime of x times f of x all over g of x squared. And unsurprisingly, the proof of the quotient rule looks a whole lot like the proof of the product rule. So if I've got my f at x over g at x, and I want to take the derivative of that quotient function, by definition that's the limit as h goes to 0 of f at x plus h over g at x plus h minus f at x over g at x all over h. Which, after a little bit of fancy rearranging, becomes the limit as h goes to 0, 1 over h times f at x plus h times g at x minus f at x times g at x plus h all over g at x plus h times g of x. I'm going to do that trick where I add and subtract the same thing from the top and bottom. So on the bottom we're still going to have g at x plus h times g at x. And on top I'm going to take my f at x plus h times g of x and I'm going to subtract f at x times g at x. Then I'm going to add it again, f at x times g at x. And I'm going to subtract the f at x times g at h plus x term. Now with some more fancy rearranging, we see, still with the g at h plus x on the bottom, we see now on top we've got g at x times f at x plus h minus f of x. We've got minus f of x times g of x plus h minus g of x. This is starting to look a little bit familiar. So now as we take all those limits, on the bottom, as h goes to 0, g at x plus h just becomes g at x, so on the bottom we've got g of x squared. And on top, the limit as h goes to 0 of g of x is just g of x. And the limit as h goes to 0 of 1 over h times this f term is f prime at x. Over here, the limit of f at x is still f at x, and all this stuff in the bracket collapses to g prime at x. And there we have the quotient rule. Although typically you see it written in the order f prime at x times g of x minus g prime at x f of x all over g of x squared. And back here I'll just do another quick example. So let's say my function is 3x plus 1 over 2x squared. So in the context of our little definition, this is my f and this is my g. So to get f prime at x, we take the derivative of f, which is just 3, times g of x, which is 2x squared, minus the derivative of g, which is going to be 4x, times the original f function, 3x plus 1, all over g of x squared, which, after some boring manipulations, becomes something like this: minus 6x squared minus 4x over 4x to the 4th, which simplifies down the rest of the way. We can take out a 2x on the top and on the bottom to get minus 3x minus 2 over 2x cubed. And there's our final result. So there you have it. Now if you ever need to take the derivative of a quotient, you have the quotient rule. The chain rule is the last rule I want to talk to you about, but it's probably the most important because it comes up all the time. The chain rule is for deriving composite functions, by which I mean, let's say I've got some function f that's a function of another function, g of x. For example, let's say I've got f of x is equal to 2 times x plus 3 squared. I could say the x plus 3 in here is my g of x, and f is a composite function, f of g of x. If we call f of x 2u squared, where u is equal to g of x. Clear as mud, right? Anyway, you'll get the hang of it. The rule, simply put, if I've got my composite function f of g of x, the derivative of f of g of x is the derivative of f with respect to g times the derivative of g with respect to x. So if I'm using my f of x is 2 times x plus 3 squared here, that just gets me df by dx is equal to df by dg. So if x plus 3 is my g function, the derivative of f with respect to it is just going to be 4 times g to the 1. And the derivative of g with respect to x, well, the derivative of x plus 3 is just 1. So my overall derivative is simply 4 times x plus 3. Now the proof of the chain rule, the proof that it works, is actually quite long and involved, and I don't think it's really necessary, so I'm going to give you an intuitive proof or an intuitive explanation for why it works. So I'm just going to draw a function here. Say, here's my function, f of x. And we're just going to think about what happens if we mess with this x, with what's the argument of my function. So like if this is x, f of 2x is just going to be smushed because everything's going to happen faster. So that's what f of 2x looks like. And at any given point, right, if I have the slope of f at x here, the slope of f at 2x is going to be twice as big. So in a way, right, the composite function f at 2x has as its slope the slope of the original function times the slope of what's inside. And if you generalize that up to derivatives, which are just fancy instantaneous slopes, then it does make sense that the derivative of a composite function should be the derivative of the outside function with respect to the inside times the derivative of the inside function. If you're interested in seeing the detailed proof, I'm going to put a link in the video right here. Logarithmic functions show up quite a bit in population biology, so I'm just going to remind you of a couple of important derivatives to know. Say my function is the natural logarithm of x, ln for natural logarithm as opposed to log, which is vague. So the derivative of the natural logarithm is just 1 over x. And for any logarithm, regardless of base, of where my function is log base a of x, then the derivative of that function, log base a, is equal to 1 over x times the natural logarithm of a. Exponential functions are closely related to logarithmic functions, right, because they're inverses. So one of the most famous derivatives is the derivative of e to the x is itself e to the x, and that's actually intimately tied to what the definition of e is. And Salcon has a really good derivation of it, so I'm just going to link you out to him and not bother doing it for you. And relatedly, in a more general sense, for exponential functions with other bases, the derivative of a general exponential function of some base a is still a to the x times the natural logarithm of the base. You're going to use these a lot, so you should just remember them. And finally, there's a whole lot to learn about derivative of trig functions, but for actual practical uses, you're only ever going to really need to know that the derivative of the sine function is the cosine function. And the derivative of the cosine function, d by dx of cosine of x, is negative of the sine function. And if you have trig functions and something you're trying to derive, you'll be able to get at it with some combination of these. I just thought I should mention it because every once in a while in population biology, something has cycles, and so we wind up with a sine or a cos.